Section 7.4, the with functional calculus. Let G be an open subset of C, and let omega gamma be a rectifiable curve in G. Suppose that f is a continuous function defined in a neighborhood of gamma with values in x. Then integral over gamma of f is defined as the limit in x of the sums of the form sigma j over j. Here we have gamma of Tj minus gamma of Tj minus 1. F gamma of Tj, where T0, T1 through Tn is a partition of 0, 1. So we are talking about this. The limit, the integral is the sum of the limit of this. It is defined as the limit of this sum as this quantity goes to 0. The quantity is the maximum of absolute value of Tj minus Tj minus 1. So the integral is defined to be the sum of this. This is exactly the same as the integral is the same as the integral for scalar functions. And the existence and the uniqueness of this limit is the proof of the existence of the limit is the same as in the scalar case. So we are not going to repeat the proof here. We just point out this limit exists. The reason it exists is that this f is continuous. We do not need analytic or holomorphic. We only need f to be continuous. Then this limit exists. And it is defined to be the integral of f over gamma. Another thing we need to point out is that this integral depends on the orientation of the curve. If we reversed the curve, we get a negative sign for the integral. So in calculus courses, for line integrals, we have the first kind and the second kind. The first kind is the integral with respect to arc length. So that one is independent of the orientation. Now, here the integral is not the first kind, it's of the second kind, which depends on the orientation of the curve. So then it is easy to see that for every functional x star in script x star, if we take the integral, then we apply x star to the integral is the same. This is equal to we take the inner product form first, then we take the integral. Again, this proof is just the kind of the proof of this equality is straightforward, or we say that it's kind of a definition. You just trace the definition, that nothing is deep here. Now we have Cauchy's theorem 4.1. If X is a Banach space, G is an open subset of C, F is from G to X is an analytic function. So please notice that this is a vector valued analytic function. And the gamma 1 through gamma m are closed rectifiable curves in G, such that the sum of the widening numbers is 0. The sum of the widening numbers with respect to A is 0 for every A in the complement of G. Then the sum of integral over gamma j f is equal to 0. This is called Cauchy's theorem. This statement is exactly the same as the corresponding theorem in complex analysis. For example, is in our textbook complex analysis by Alfors. So yeah, there we also use the winding number, etc. So here we give a proof. The proof we do not use that we do not repeat the proof for the scalar case. Instead, we use the proof. We use the result of the scalar case. So if x star is in script x star, so x star is a continuous functional on x, then we take this. We take this. We take the integral inner product with integral comma this x star. So that means the function, the value of the functional on this vector, and this is the same as we take the inner product form first, then we integral. Okay. If we after we take the inner product form and this integrand is an analytic function. It is an analytic function. So after so if we take the analytic function here, then we take the inner product form with the continuous functional, then this is an analytic function. So then we use scalar case of Cauchy's theorem. Then this, and then for this analytic function, we can apply scalar case of Cauchy's theorem. We get 0. So this says that for this integral, you take the inner product with any continuous linear functional, you get 0. Then this must be 0. So this must be 0. And this is the proof of Cauchy's theorem. Then we have this Cauchy's integral formula 4.2. If X is a Banach space, G is an open subset of C, F is from G to X is analytic, gamma is a closed rectifiable curve in G. By the way, rectifiable means it has a finite length. Okay, has a finite length. So of course, the length of a curve is defined this way. You take the partition of the point on the curve, then you calculate. You take the sum of the small segment. Okay. Then Then this is a sum. Then you take the soup of such sums, that is the length. Okay, for this rectifiable curve, then the length is finite. Okay, rectifiable means finite length. So gamma is a closed rectifiable curve in G such that the widening number is 0. Widening number is 0. And also this rectifiable is the condition to define the integral. Okay, so yeah, if the curve is rectifiable, if the function is continuous, then the integral exists. So this rectifiable is a necessary condition. Now, of course, if it's a piecewise differentiable or piecewise C infinity or C infinity, then all of these curves are rectifiable. Rectifiable is a relatively weak condition. It's relatively weak compared to like C infinity or C2 or C1. It's weaker than C1. Is weaker than C1, weaker than piecewise C1. Okay, but it's stronger than continuous. A continuous curve may fail to be rectifiable. So this gamma is a closed rectifiable curve in G such that the widening number of gamma with respect to A is 0 for every A in the complement of G. And suppose lambda is a point in G, which is not an gamma, then for every integer k greater than or equal to 0, we have this. Again, this formula is very much similar to the corresponding formula in complex analysis. And the proof is very similar too. So we are not going to repeat the proof. So we put this sign here, that means we are going to skip the proof. There's no proof for this theorem. So now, if gamma, big gamma, is equal to gamma 1 through gamma m is a collection of pairwise disjoint simple closed rectifiable curves, then gamma, we say, is a positively oriented path. Then we could say curve, but the path suggests that, emphasize that it has a direction. Okay. Then gamma is a positively oriented path if two conditions are satisfied. For A in C minus gamma, the widening number of gamma with respect to A is either 0 or 1. B, the outside of gamma defined by, so if this gamma, the widening number is either 0 or 1, then the outside is for widening number of 0 for the points with respect to which the widening number is 0, that is outside. If the widening number is 1, that is inside. So condition B is that the outside of gamma contains unbounded component of C minus gamma. So C minus gamma, okay. So gamma is a path, okay. So in particular, it is a compact set. It is a compact set. For compact set, then C minus gamma is an open set. This open set has several components, maybe one, maybe more, okay? But there's exactly one component which is unbounded. So C minus gamma has exactly one component which is unbounded. So that is the unbounded component of C minus gamma. So the outside of gamma contains the unbounded component of C minus gamma. So that is a condition B. We have two conditions. A is this, okay. Condition A says that the Widen number is 0, either 0 or 1. Condition B says that the outside of gamma defined by Widen number is 0 contains the unbounded component of C minus gamma. Then the inside of gamma is defined by this equals 1. So proposition 4.4, if G is an open subset of C and K is a compact subset of G, then there is a positively oriented path. Gamma is, so here we write gamma is equal to gamma 1 plus gamma m. This is just the new way to write exactly the same thing. So gamma consists of these several simple curves. So in G minus K, so K is a compact subset. So gamma is a path in G minus K. This just means gamma and K do not overlap. Then such that K is inside gamma. K is contained in the inside of gamma. And the inside of gamma is contained in G. Okay. The path gamma can be found such that it is infinitely differentiable. So gamma can be found such that it is infinitely differentiable. So if K is a compact set in gamma, we can always find a positively oriented path to surround it, okay? To surround it, so that K is inside of that gamma. Again, if it needs a proof, the proof is in complex analysis. Let A be a Banach algebra with identity, and Banach algebra with identity, and let A be a vector in script A. If F from G to C is analytic, and the sigma of A is in G, we will define an element FA in script A. Now, please, this is a very crucial here. It is crucial here. So F is an analytic function from G to C. So the variable for F is Z, okay? A complex number in G. Now we have a value F of Z. So for a complex number in G, we have a value F of Z. But now we want to define F of A. So this is a new notion, okay? So F originally is a function on complex numbers. Now we put this A, this vector, in the slot for variable. So we want to define this FA in script A by the following formula. The formula is this. f of a is equal to 1 over 2 pi I fz z minus a inverse dz. Please notice that if this a, we replace this a by a complex number zeta, and if zeta is inside gamma, then we have this formula. Okay, so if zeta is a complex number inside gamma, we put the zeta here and the zeta here, then this is the correct formula. But now we replace that zeta, we put a here. A is a vector, is an element in A. And this is not a formula. It is the definition of FA, because we don't know the meaning of A yet. Okay, we do not yet know the meaning of FA. So this is the definition of F of A. And the right side integral is well defined. We use this to define F of A. But the first thing is that we needed to show that this is well defined. That is, we have to show that this integral is independent of the choice of gamma. Okay, so where gamma is an infinitely differentiable positively oriented path in G such that sigma of A is inside of gamma and which belongs to G. We say infinite differentiable because in the previous proposition we say we can always find such an infinitely differentiable positively oriented path. But in fact, the gamma here, it's no harm to say infinitely differentiable, but actually this definition works also for just the rectifiable. Okay, perhaps I should put it is better to put the rectifiable here. But anyway, so now we want to prove that this is well defined. So the integral one, the proposition 4.6, the integral one does not depend on the choice of gamma. It does not depend on the choice of gamma. Proof, suppose that gamma and lambda are two positively oriented. We have two of these. We want to prove that the integrals are the same. So suppose gamma and lambda are two positively oriented paths in G, satisfying sigma A is contained inside of gamma, and which is contained in G, and the same thing is true for lambda. We would like to show that the integral is the same for gamma and lambda. So then we are going to take U, okay? U is the G minus sigma of A. So U is an open region, okay? Because G is open, sigma of A is compact and hence closed. So U is open. And sigma is equal to gamma minus lambda. Gamma minus lambda means gamma plus lambda with reversed orientation. So we say gamma plus lambda with reversed orientation. That is gamma minus lambda. Then we have this n sigma, winding number of sigma with respect to z for each z in the complement of U in C. For each z in the complement of U in C. So now, let me convince you, this is 0 for each Z in C minus U. If Z is in C minus U, then there are two possibilities. One possibility, possibility number one, Z is outside of G. And possibility number two, Z is in sigma of A, because U is G minus sigma A. So if Z is in C minus U, there are two possibilities. Possibility number one, Z is outside of G. Possibility number two, Z is inside, Z is in sigma of A. So we want to convince ourselves in each of these cases, the White number is equal to 0. Now, case one, Z is outside of G. Okay. In that case, the White number sigma is equal to White number of gamma minus White number of lambda. Both terms are equal to 0. So this White number is equal to 0 minus 0 is equal to 0. Case number two. This Z is in sigma A. Then this White number is equal to White number of gamma minus White number of lambda. So it's equal to 1 minus 1. Both are inside, that means White number 1. So this White number is 1 minus 1. So it's equal to 0. So this assertion is correct. So the White number of sigma with respect to Z equals 0 for each Z in C minus U. Okay. Since the vector valued function is analytic in U, okay? This is not analytic on sigma of A, but the sigma of A is removed here. So this is an analytic function in U. And this path has White number with respect to Z for every Z outside of U. So by Cauchy's theorem, this is equal to 0. That means the integral over gamma equals the integral over lambda. So the integral is independent of choice of gamma. So this f of A is well defined. So the proof, we have finished the proof of this proposition, okay? So this one, just a formula I showed you earlier, gives a well-defined element f of A, of script A, whenever f is analytic in the neighborhood of sigma A. Then for functions analytic in the neighborhood of sigma A, we have a notation. So how of A be the set of the functions that are analytic in the neighborhood of sigma A. So we use HOL because analytic function is also called holomorphic function. So HOL is the first three letters for the word holomorphic. So this is that Hall of A is the functions analytic in the neighborhood of sigma A. So this is an algebra because it has addition, multiplication, and scalar multiplication. So it is an algebra. So now we have Riesz functional calculus 4.7. let A be a Banach algebra with identity, and let A be in script A. Then A, the map F maps to F of A of Hall of A to script A is an algebra homomorphism. Algebra homomorphism, this just means that first is linear transformation. Then for the product, it maps the product, the image of a product is the product of image. So that is algebra homomorphism. So homomorphism means it keeps the algebraic structure. B, if f of z is equal to an infinite series, and if the series has a radius of convergence greater than R of A. Remember, this R of A is that spectral radius. So it's a maximum of W, absolute value of Z, where Z is in the spectrum. So then F is in Hall of A. Of course, this is analytic in the neighborhood of sigma of A, okay? So then FA actually is equal to, you just replace this Z by A. C, if Fz is equal to 1, so Fz is the constant function, then f of A is equal to 1. D, if Fz is equal to Z, then f of A is equal to A. E, if F1, F2 are analytic functions on G, sigma of A is contained in G, and if F and Z goes to F of Z uniformly on compact subsets of G. So here we are talking about the convergence of analytic functions. This is this kind of convergence is very much used. Okay, so this goes to Fz uniformly on compact subsets of G. Then Fa, Fn of A minus Fa norm goes to 0, as n goes to infinity. Okay. Proof A, it is clear that F maps Fa is a linear transformation. So that part we don't have to prove. The only thing we needed to prove is that it maps products to products. So it suffices to show that if you have two functions, then you have Fg is a function. You use this Fg to define Fg of A is just equal to F of A times G of A. So this is the only thing we needed to prove. And it is not that obvious. Okay. It is very obvious that it is a linear transformation, but this, what we have to prove is not that obvious. So let Fg be in Hall of A. That means they are analytic in the neighborhood of the spectrum of A. And let G be an open neighborhood of sigma of A on which F and G are analytic. So here, F is defined in the neighborhood. G is defined also in the neighborhood of the sigma A. So F and G are both defined in intersection of the two neighborhoods we mentioned. So for any two members f of g, we can always find a common neighborhood on which these two functions are defined. Okay, so on which these two functions are analytic. So we have a neighborhood on which these two functions are defined and analytic. So let gamma be an infinitely differentiable positively oriented path in G such that sigma of A is contained in the inside of gamma is inside of G. The existence of such path is guaranteed by an earlier proposition. Okay, so we can find this gamma so that sigma of A, the spectrum, lies inside of this gamma. Then we get another path, lambda, so that gamma is inside of lambda. So that lambda be an infinitely differentiable, positively oriented path in G, such that the closure of inside of gamma is contained to inside of lambda, which is contained in G. By the way, the closure of inside of gamma is just the inside of gamma union gamma itself. Okay, then we are going to go through a sequence of calculations. Okay, so then f of a g of times g of a is equal to this. So this minus 1 over 4 pi squared, this is just 1 over 2 pi I times 1 over 2 pi I. You know, in the definition of this f of a, we have 1 over 2 pi I. This 1 over 2 pi I comes from in the Cauchy integral formula. So we have seen this many, many times with complex analysis. So this is just the square of this 1 over 2 pi I. Okay. Then for f of a, we write this way, f of z, c minus a inverse dz. And this integral is on gamma. And g of a is equal to integral over lambda, g zeta, zeta minus a inverse d zeta. So yeah, so we can write this because this integrals, the definition for f and g are independent of choice of the path. So we choose gamma for a, we choose lambda for g. Then we are going to write this as an iterated integral. We are going to write this as an iterated integral. We write this as an iterated integral. So this means that we put this together, we multiply, then we integrate the whole thing with respect to zeta first. We integrate the whole thing with respect to zeta on lambda. Then we integrate the result with respect to z on gamma. Okay, so we have this. Then this part can be rewritten like this. Okay, so this we can verify directly if A is a complex number, then we can verify this easily because we just change these two fractions to common denominator. So then we change this to common denominator. Yeah, we start from this integral. We change this to common denominator. So the denominator is z minus a times zeta minus a. and the numerator is just zeta minus z. Then we cancel this, so we get that. So if A is a number, this is equal to that, and it is easily, straightforwardly verified. But now A is not a number, and this is still true because the manipulation still works, because this Z minus A inverse commutes with zeta minus A inverse. Okay, first that we think this way, okay? We do not use any theorem. We do not use a scratch paper. We just think this in mind in the following way. First, if X commute with, so any number commutes with any vector. So that's why Z minus A, Z commute with A, okay? Because Z is just a number. And Z minus A commute with zeta minus A. Because the only vector involved is just one vector, A. Z and zeta, just numbers. And also, we have the following fact. Let me tell you this. If Z commute with Y, and Y is invertible, then if X commutes with Y and Y is invertible, then X commutes with Y inverse. This fact is easily verified. So, in other way, so since this A commute with A, so Z minus A commute with zeta minus A, and the inverse, by the principle I mentioned, this inverse commutes with this inverse. So therefore, actually, we can treat this very much like, we treat this in the way very much like in the scalar case. So that's why we get this result. So now we have this iterated integral, double integral. Now we are going to write this as an iterated integral in two different order. Okay, for this term, so we have two terms. Okay, these other things are common factor. So this one term is Z minus A, the other is zeta minus A. Okay, for Z minus A inverse for this term, that's the first term. We write the iterated integral in this order, same order. We integrate with respect to zeta first over lambda. Then we integrate with respect to z over gamma. So we do not change the order for the first term. But for the second term, we change the order. So you have minus, so you get a plus here. But for the first term, if we do not change the order, we write this as 1 over 2 pi I times 1 over 2 pi I. So this iterated integral is written as the sum of these two terms. Let us look at the first term. For the first term, okay, for the first term, this for the Cauchy integral formula, this is equal to g of z. For the Cauchy integral formula, the inside integral equals g of z because this z is on gamma, because this z is inside of lambda. This z is inside of lambda. So the inside integral is equal to g of z. For the second integral, we integrate with respect to z first, okay? Then this integral is 0 because this zeta is on lambda, because zeta on lambda is outside of omega, outside of gamma. So zeta on lambda is outside of gamma. So this is 0. We need to keep inside. Gamma is inside of lambda, and lambda is outside of gamma, okay? So because lambda is outside of gamma, so zeta is outside of gamma, so this integral is 0. So therefore, these two terms are equal to this. The second term, you get 0. The first term, because inside the integral equals g of z, we get that. And by the definition, this is just the f of g together of a.